Okay, in the next problem we have a differential equation dy dx equals 3 minus x over y. Let y equals f of x be the particular solution to the given differential equation for x is between 1 and 5, such that the line y equals negative 2 is tangent to the graph of f. So we want to find the x-coordinate of the point of tangency and determine whether f has a local max, local min, or neither at that point, and justify your answer. So if y equals negative 2 is tangent to the graph of f, y equals negative 2 is a horizontal line, and if a horizontal line is tangent to a curve, then that means that there has to be a zero derivative at that point. So we take our derivative, set it equal to 0, and just plug in y equals negative 2. And we can see that solving that will give us x is equal to 3. Now we have to determine whether there is a local min, a local max, or neither. Now we could use the second derivative test here, and we would find the second derivative and then plug in x equals 3, y equals negative 2, and y prime is equal to 0, and that would tell us. We can also, in this case, it's really not too difficult to do a simple sign chart. We know that at x equals 3 we have a zero derivative there. So all we need to do is to find a value a little bit to the left and a little bit to the right. So if we plug in a value a little bit less than 3, then you should see that we will get a positive numerator and still a negative denominator, so that will turn out to be negative. We plug in a value a little bit larger than 3 for x, and we're going to get a negative value in the numerator, a negative value in the denominator. That will give us a positive value. And so that would indicate that we have a minimum there. As I said, you could just as easily find the, well, you could also find the second derivative using the quotient rule and implicit differentiation. Plug in x equals 3, y equals negative 2, and y prime is equal to 0, and you should see that you also get a value that is positive in that case for the second derivative, indicating that the original function is concave up there at x equals 3, y equals negative 2, and since we know there is a zero derivative there, then it has to be a minimum there. Alright, so now a sign chart is never sufficient as a justification, so we still have to put our conclusion into words. So we have to state that explicitly. But we don't need to say much more than that. By the first derivative test, there's a local minimum at 3, negative 2. Second, we have a particular, we're looking for the particular solution for x is between negative 2 and positive 8 with the initial condition g of 6 is equal to negative 4. Now every different particular solution, or every different initial value, every different initial condition will produce could quite conceivably produce a different particular solution, and so we call it something other than f of x each time. So this is g of x. So we start with our differential equation. We're going to separate variables, integrate both sides with respect to x. When we do that, we'll end up with y squared over 2, and on the right side we get 3x minus x squared over 2 plus c. If I multiply through both sides by 2, I end up with y squared as 6x minus x squared plus c. I take the square root of both sides. Now I'm going to plug in my initial value, although I could have done it earlier as well. So when I plug in x equals 6, I get 36 minus 36 plus c. And since that has to come out to be negative 4, I only use the negative value there outside of the square root. And so c is going to be 16. And that does it for this problem. On the side, I'm going to provide us the alternate solution to the second part of part A. Find the second derivative of that derivative using the quotient rule. But because y prime is 0, we simply end up with negative y over y squared. So I should be plugging in y as negative 2 from part A. And I state by the second derivative test there's a local min there.